once again to this channel. So in the last video we have designed one sodium manganese hexacyanoferrate, that kind of cathode material, like how to design the unit cell of that material, that we have seen. So I am also opening the same structure what we have designed yesterday. So this kind of structure we have designed using our materials project and Vesta software. So you can see here we have kept the sodium atoms on the body, on the face center position of this particular lattice. Next, if you want to do the optimization of this kind of structure where you are having carbon, nitrogen, ferrum, manganese and also sodium in between, so how we will, which kind of method of the DFT that we will use, so all these things we will see today. So as we know that in this structure we are having manganese and ferrum, both of them are transition metals. So why they are transition metal? So here I have searched for what is the electronic configuration for Fe and also Mn. So you can see that for Mn this electronic configuration is argon 3d5 4s2, and for Fe it is argon 3d6 4s2. That means all these two metal atoms are having one unfulfilled d orbital. So this is, that's why they are representing the transition element. And so for transition element the normal DFT calculation will be little different. So for that specifically we use the Hubbard correction factor. So here I am opening the INCAR file for the same. So as we know that these are the standard DFT optimization parameter, where we know that this is the system specification, that I start, that we don't have any charge curve file, previous charge curve file to start with, normal precision, all these things we know. This is the energy cutoff, this is the number of electronic step, and ISIF2 means no volume change, and all other parameters we have already know. This we know, and we have also discussed in the earlier lectures of this VASP tutorial, like in the first and second lectures. Next, here we will go a little specific towards this kind of calculation, which will lead us to the calculation for the transition metal. So in the second section you can see that here the I spin is equal to 2. I can also open the VASP manual on the side so that it will be easier for us to catch everything. So here we have taken this I spin 2. So I spin 2 is mainly due to this which will do the spin polarized calculation. Here also I will search everything, I spin. So I spin 2, which specifies the spin polarization. So as these are metal where, like, these are the transition metal element where we can have the spin polarized calculation because of their magnetic movement, because they are magnetic elements. So for that we should utilize our spin polarization calculation. And in the next one, this is magmum will define the magnetic moment. So as you can see that these here we have defined what are those elements and what are the value of magnetic moment. So first I will show what is the specification for the magmum. So here magmum, if I am searching, you see that magmum has a tag like n ions into 1.0, where this 3 into n ions into 1.0 for non-collinear magnetic systems and all. So what it is suggesting, that magmum can be specified as number of ions that are present, like the number of atoms or something that we have taken in our postcard, in that order. And here this is nothing but the value of the magnetic moment. Okay, so here I can also show that what is the postcard file. So here I will again go to this postcard file. So you can check that in the postcard file the atoms are represented like 8 sodium, then 4 manganese, 24 ferrum, 24 nitrogen and 24 carbon. So in the similar pattern we have taken here 8 into 0 0 because sodium is non-magnetic, and then 4 into 5.0. So here 4 is the number of manganese atoms present, and 5.0 is the magnetic moment value for the manganese, and here 4 representing Fe, then 2.0 for Fe, the magnetic moment for Fe, then 24 into 0 and 24 into 0 because this carbon and nitrogen are also non-magnetic, here we have taken. Okay, so this way we have specified that what are the magnetic moment. Also one thing need to notice that here we have taken the maximum for manganese as 5.0 and for Fe it is 2.0. So it is, as we have also discussed in the last video, that this manganese can be present on the high spin state and ferrum can be present at the low spin state. It can be differ, you can also do the reverse thing as well. So if you have specified your manganese for a high spin state, then you can have this maximum value little higher, so that it will specify that manganese is at high spin and this ferrum is at low spin due because of the like the little value for the maximum. Okay, so this way we can define that which one will be where and which one will be in high spin and low spin. So how to define, how to guess these values, initial values? So for that, here I can also show you that you can check that this Fe is this magnetic moment is also related to the oxidation state and the number of unpaired electrons present. So for Fe the magnetic moment value is 5.92. however this 5.92 is very high, that means it will correspond to a high spin state, but here we have taken 2.0 which is also reliable for a low spin calculation. So this way you can search and you can calculate based on their unpaired electrons their respective magnetic moment, you can calculate in this method. Okay, next part is the L orbit. So what is this L orbit? We can also search it over here. So L orbit will suggest that such a projection method on local quantum numbers. So the value of 11 will shows that the DOS, it will write the DOS car, so the and pro car that we can use for our further calculation. You can also see that what is this L orbit greater than equal to 10, that means 11 is also here in this case, what it will represent. So based on this you can see, I think we have already discussed about this kind of tags. Next we will simply come to this DFT+U, that is mainly necessary for this transition metal elements. So here simply I will search this DFT+U here. So you can see that this DFT+U things came. So this is nothing but you can see that this is the exchange correlational function, and here the correction has been added to it. So this way this is the energy expression for the correction in terms of the DFT+U method, and this is a method which was proposed to improve the description of a system with strongly correlated D or F electrons. As we have seen that manganese and ferrum have this D element unfulfilled D element like D orbital. So for that we are using this particular method so that we can rectify their strongly correlated issue that are happening between the D electrons or D orbital electrons. Okay, so this way we have progressed. Then next, it also has certain different tags. In order to specify that DFT+U has to be switched on, we should use LDA+U. So here you see I am clicking over here. So this LDAU will be true. So if we are calculating any transition element or optimizing any transition element, so here this first tag is this one has to be true. Next is LDAU type 2. So what is the meaning of that? So LDAU type, so here I am searching, you see that LDAU type 2 which will specify that it has a simply rotational invariant approach for the DFT+U, and this is also a default tag. You can go ahead with the type 2 like 2 value. Next, what one which one we want? Next is this LDAUJ. LDAUL. So what is this LDAUL, that we will see here. So you can see that LDAUL will define the number of types into 2, so which specifies the L quantum number. Actually, you see that here we have sodium. So sodium, if we will see the electronic configuration of sodium, so how much it will come. Here I can search like sodium. So this is ns1. So for s value, so this LDAUL value L will not be turned on. That means this should be in the negative value. So for this value, you see that LDAUL equal to -1, no on-site interaction is added. If we don't want any interaction from the sodium, then we should simply add that LDAUL is equal to -1 for that particular element. So here, corresponding to sodium, we have set it as -1, and for carbon nitrogen also we have set that as -1 and -1, because they don't have any on-site d correlate, like d orbital to for this correlation. But for this manganese and ferrum, we have set this value as 2. Okay, this is because they have some on-site L orbital quantum number that will come for the interaction between the d elements and all. So for that, we have turned it on as 2 value. Next is LDAUU. So what is that? So here you can see that LDAUU type will sets the effective on-site Coulomb interaction. So this is also known as U value. So U value for each different element is differed. So many researchers have shown this kind of results, that what is the best calculated or best known value of U for any particular atom or element. So there are so many research paper. So after getting 1-2 reference paper, those who have used this much value for manganese and this much 4.3 for Fe, we have set this value for our case like this. And so you can also take and all other those who are having LDAU value equal to -1, we have said that 0 for all of them. And for manganese, this value we have set as 3.0, and for ferrum we have set it as 4.3. Okay, next one is what? LDAUJ. So here you see, so what is this LDAUJ? So it shows that it sets the effective on-site exchange interaction. So U was the on-site Coulomb interaction and J was the on-site exchange interaction. If you don't want to give any exchange interaction, so you can see also here that this J is nothing like the at the end the entire value will be calculated as U minus J. If you don't want to give your J value, then it will be simply take U minus J, which is even 0, that means simply U. So if you don't want to give J value, that is also completely fine. You can simply set all your values to 0 0, and as a whole you will get your U value at the end. Okay, next one is what is LDAU print. So here you can see that this LDAU print you have to set how much. Here we have set it as 2. So why is that? Because it controls the verbosity of DFT+U calculation. That means the this here, if you are taking 0, that means no on-site occupancy matrix will be written on the outcar file. If you are taking 1, the spin up and spin down on-site occupancy will come. And if you will take even more, then it will also shows that the spin up and spin down calculation. You can also mainly this 2 value I think it used because we are having d orbital electrons. And also if possible we can also take this value as 1 even. So you can also see some example tag later, that we will show later. Next one is the L max mix, that is equal to 4 we have taken. So let's see what is that. So L max mix is equal to 2, which is a default value here, which suggests that higher L orbital quantum number, this L can be greater than L max mix. Mainly you can see that L max mix is equal to 4, mainly for d electrons, as we are having manganese and ferrum which are having d electrons, so for that we have taken this as 4. Okay, and it has 6 for 8 and 6 for F elements and so on. Next, this lapse. So that can be, that I can search over here. So what is that? LASPH. So this will suggest that include non-spherical contribution related to the gradient of the density in the power sphere. So particularly in the case of a DFT+U kind of hybrid functional, people use this LASPH is equal to true. This is essential for accurate total energy and band structure calculation for F element or all 3D element and like that. So we have set all our parameters for this DFT+U. Now we can also try to search some example tags, those who have used this kind of LDAU, LJ and this kind of terms. So here one I can open. So here you can see that they have used this LDAGGA+U kind of parameter, and here they have taken LDAU print equal to 1. So now I am confirmed, so I am going to change this value to from 2 to 1. So you can so as it was given only 0 and 1 value, so I am changing it to 1. Next, so this way you can find some example tags also, and those values you can also use for as per your reference. Okay, and next, this section we are also familiar with. This is showing the mixing parameters. So here I am also going to this VASP. Here I can search some mixing parameter, density mixing. So here if I will go to this mix mag, so you can see that this is a standard value like that provided by the VASP community. You can see this you can simply use for sometimes what happen, using this kind of correction factor take very long time for the optimization. If we will use this kind of parameter, so we can get our results within very less time. So this will try to faster the calculation. So for that we have used this kind of density mixing parameter. And okay, now with all these parameter setting, we have set our incar file, and similar way you can also set your k points. So here the k points I have set like gamma points 444, as this is a cubic value, so along all the 3 direction we are having same number of gamma point value. Next is the port card, so that I can show you like grape title port card, where we are having sodium, manganese, ferrum, nitrogen and carbon. Okay, so similar way we have in our postcard file. Now with this you can submit your simulation, and for this kind of particular structure to get this like optimized result and all. Okay, so I hope you guys have understood, and this much for today's session, and thank you all.